Good afternoon, everyone. Can someone remind us what we discussed in the previous lecture? We discussed about calibration. Why did we discuss the topic? Why is the topic relevant to this course? Anyone? Why should we be studying calibration in a probabilistic machine learning course? We are not building instruments. Anyone? Okay, I'll have to handpick people now. Okay, we'll start with the latecomers. Dhairya, why are we studying calibration in this course? It's not a difficult question. I think all of you know the answer. Okay, second latecomer. Rahul, why are we studying calibration? Okay. Anyone? Sorry? To compare the models. Okay. What does a well calibrated model mean? Anyone? So what was the example we studied last time? Forget about models. Rain, right? We discussed that if the weather forecast says, let's go back. Why do I keep picking up New York for this example? You have certain rain there. If I look at Gandhinagar, it will be 0% chance of rain, right? So it doesn't add much. Look at Saturday, precipitation. Okay, 7 a.m., 40% chance of rain. We discussed this last time. Now can someone get the context and tell what this means? When would we say that their predictor or their classifier is a good classifier?
Among all the times that they have predicted 40%, about 40% of that occurrences is rain.
Okay, excellent. So they say that the chance of rain here is 40%. We look at all instances where they told the chance of rain to be around 40%, and around 40% of those times it rained. Right? Fairly simple concept. We looked at this problem for a 2-class calibration. We looked at for a multi-class calibration, and then we looked at for regression. We are looking at these sort of miscellaneous topics. We could have done them at the end, but because of the large gaps you are having between these classes. Now again we have a class now, and then after a long time we will have the next class because of exams. So there was no point in picking up the next logical topic in sequence, which would have been variational approximation, which is another way to get uncertainty or to get the posterior distribution. Right? But instead today we will be looking at yes. Can you be a little louder? I mean, it's not an instrument in the traditional physical sense. Like it's not like a thermometer, right? You can think of mapping, but it's not a traditional ML instrument where you're using. So traditional instruments are used for observations, whereas machine learning models are used for predictions. Now you could think of the traditional instruments also have a prediction function built, but it's in the traditional sense the notion of instrument is observation, whereas for this it's prediction. Okay, so how do we get uncertainty out of neural networks is what we want to study today. Have you already studied this topic? How can we get uncertainty out of neural networks? Okay, Arjit, how do we get uncertainty out of a neural network? If you have weight as a distribution and then? So you say that we can solve the neural network for not just point estimates, but how do we solve that? Like, so you have told one part of the entire aspect of getting uncertainty in our predictions, which is to assume a distribution over weights instead of point estimates, but that is not enough. Right? That is the basics of it, but how do we solve it? How do we actually get these distributions? For Gaussian distribution, we are talking about a neural network.
Yeah, I'm saying if you're modeling weights as Gaussian distribution.
So you want to model weights as Gaussian distribution, okay, and then?
So we have two parameters.
So typically we don't say we're modeling weights as a Gaussian distribution. We want to be thinking, so I want the answer more in the Bayes world of view, right? We set a prior on the weights, which is typically a Gaussian distribution, but could have been anything else. Okay, how do we get the posterior? That is my question. So in Bayesian linear regression, we solved the integration, but we can't solve it here. So therefore, we can go for gradient descent. No, gradient descent is just an optimizer, right? You can use gradient descent to get the map, theta map, but you can't be using gradient descent to get the whole posterior. Like you won't get, like, you can technically use it in something we'll study later, which is a variational approximation, but the techniques we've thus far used don't require that. Okay, you're there, but not exactly. Someone else? You can use Laplace approximation, or we could use sampling techniques such as MCMC, or any other sampling technique, rejection sampling, importance sampling, right? All of these we could use, and then we'll get either the approximate posterior distribution, and once we get the approximate posterior distribution, how do we get the posterior predictive? Sorry? We don't integrate, instead we use Monte Carlo estimation, and we could also get the same via just Monte Carlo MCMC also, where we don't get the predictive distribution, we don't get the posterior distribution, but instead we get samples from the posterior distribution. Okay, so these are some methods we have already discussed. What do you think about these methods? Easy, difficult? You looked at the implementation. Was it easy, was it difficult? When we had to implement Laplace, yes.
So if you want to do Laplace, then Laplace has a lot of strings attached to it. Like
Okay.
If the Hessian is positive, then
Right. So when you're dealing with Laplace, you have to firstly also deal with the Hessian matrix, and it's not trivial to do that. Even in MCMC, we saw it was a very slow procedure. Right? You had to draw in a lot of samples. So today we'll be looking at two different methods of getting uncertainty out of neural networks. You'd be surprised to see how simple these methods are. And you may also be thinking that why did we have to discuss such complicated methods when such simple ones exist, right? So my question to you before we discuss this topic, does random forest give us uncertainty? Yes, no, it has to be quick answer. Yes. Is random forest a Bayesian method? So till now, did we have this, if anyone had this connection that Bayesian equal to uncertainty or uncertainty equal to Bayesian, that you need to break. We can get uncertainty out of statistical or frequentist methods also, right? So the Bayesian methods, how would you distinguish between these two, Bayesian and frequentist? Like one example is Bayesian linear regression is a Bayesian method, or you could even solve linear regression in in that way. But in random forest, you don't really need that. How would you distinguish? The application of Bayes rule is what distinguishes them, right? You'll put a prior, you'll have a likelihood, you'll get a posterior, right? In random forest, do we do that? There are equivalents, there may be equivalents of this also, which get you Bayesian. So there are things like Bayesian additive regression trees, etc., BART instead of CART, which is traditionally being used, but we generally don't use them, right? But then we can still get uncertainty. How do we get the uncertainty out of a random forest? So we don't typically do that because in tree-like methods, we are solving discrete optimization problems. You're talking about neural networks. Okay, what about neural networks? So if you include the variance in the loss term, you are essentially talking about heteroscedastic likelihood, which is still talking only about aleatoric uncertainty. To get epistemic uncertainty or the uncertainty in the weights / the parameters, you will need to assume a prior over those weights and then feed them to the likelihood, get a posterior or an approximate posterior. So typically both things are being done, both aleatoric and epistemic uncertainty need to be encountered. Right. So we were talking about random forest, we get uncertainty out of that. What is the basic behind that?
We can use conformity scores.
You can use?
Conformity scores.
Okay, you are skipping way ahead of the queue. We will not talk about conformal prediction till we talk about conformal prediction, not today.
So for classification, we can use entropy. For regression, standard deviation.
So essentially we are dealing with an ensemble or multiple such classifiers / regressors which are built on the same data set. Right. Now, what do you think different members of this ensemble give you? Why it is beneficial? This was the previous semester's course. Why is it useful to have an ensemble?
Okay. So in an ensemble, we take something like the majority score or the average. So here the probability of all three being, as long as the probability of one being wrong is less than 50%, so that of all three being wrong is even lesser.
Okay, so we discussed in the previous semester where there were 2 or 3 main reasons which we had chosen. They give you some statistical benefits, in certain cases, for example, if you're using a decision tree of depth 1, you can only get linear boundaries, but if you use multiple of those, you can get a circular boundary also. Right? So therefore, ensemble-like methods are useful. We can get uncertainty by looking at the deviation in the predictions. Right? If you have that concept, you already have deep ensemble. That is it to deep ensemble, nothing overly sophisticated. So this is a diagram we put in one of our publications recently, 2 years back. We want to be comparing different methods of MLP and how to get uncertainty. The first is just the regular MLP. The second is what Arjit was just a couple of minutes talking back. We can put a mu and a sigma, and we can put a heteroscedastic likelihood. In this case, we are assuming a Gaussian heteroscedastic likelihood. You can get the uncertainty. The left hand side is the data. Deep ensemble trains different neural networks. That's the important thing. Independent neural networks are being trained on the same data set. Right? And therefore, for each of them, you will get a mu and a sigma as a function of the input x. Or it could have been just without mu and sigma, you could have just learned y hat as a function of x for each of the neural network. Right? And that you can then combine to get multiple predictions. Bootstrap. Where have you heard the term bootstrap before? Bagging, boosting, we heard that, right? So you can get uncertainty or you can get different members in ensemble by having the same data set, but learning differently initialized neural networks, or you could also use different subsets of data sets. And in that way also you will get different models. Right? Now, in the deep ensemble and bootstrap method, you're learning n independent models. Right? If we have n members in an ensemble, n independent models. What does that mean? The training time would be large, the memory size required would be fairly large. In contrast, the other method which we will look at today, which is called Monte Carlo dropout, it creates a same neural network, like it learns a single neural network, and it drops off nodes from the neural network using some distribution, Bernoulli distribution. And when you do multiple forward passes at test time, you will get different predictions. Right? And that's how you can get uncertainty out of it. So we will go over each of these in a bit, but this was just the main glimpse of how to get uncertainty with neural networks in various ways. We start with the simplest way, heteroscedastic likelihood, and the remaining 3 capture the aleatoric, the epistemic uncertainty. So I'll be Okay, so these notebooks have also been borrowed from this excellent course. You should definitely take a look at this course from University of Amsterdam, I believe, somewhere. So it's a yes.
And is there no general formula for uncertainty?
Is there no general formula for uncertainty? That is a very broad question. Can you narrow it down to some specific context?
Like there is uncertainty in Bayesian models. There is in conformal.
Yeah.
So for every model we are using different technique or formula to find out the uncertainty. Why can't we have just like define uncertainty somewhere and use it?
So Ritik is asking a question equivalent to having a unifying theory in physics. Like you'll have different people with different theories, but there's a lot of merit to this question. For example, now we are talking about this deep ensemble technique. Does the deep ensemble technique look like a Bayesian technique to you? There's nothing Bayesian about it, right? Right? But if that were the case, I would not be asking this question. Could you think of anything Bayesian here? Okay, hint. Dirac delta function. Think of a posterior, which can be formed by a combination of different delta functions, each of which is at the specific weights of that neural network. Right? I'll not go into much detail, but as you've asked this question, deep ensembles from a Bayesian perspective. Right? You could think of, so they've shown how this is traditionally assumed to be, deep ensembles can be considered as state of the art for uncertainty quantification. It was originally proposed as non-Bayesian technique, but this paper shows that deep ensemble can be viewed as an approximate Bayesian method by specifying the corresponding assumptions. So similar is the case when we think of regularization and putting a prior. Like we can combine both the Bayesian and the frequentist view. We can think of both of them giving you similar answers.
One more question. Like we have different methods to find out uncertainty in different models, but then we try to compare which uncertainty is better. Is there any? I don't see the sense why we are comparing if we are not sure on how to define uncertainty.
Okay, so the question is, why do we compare different models for uncertainty? You know, there are, so whenever we do any comparison, we have to have appropriate metrics. Right? So there are a few appropriate metrics which are used to quantify uncertainty. One of them being the calibration score, right? The coverage. There are a few other. One of them being negative log likelihood, right? Which just does not look at only the point estimate, but also the variance in it. So there are well specified metrics for looking at uncertainty. There are well specified tasks which can tell you whether or not you're doing good in out of distribution versus in distribution settings, and therefore we can do a valid comparison. So we'll have to look at some of these papers. For example, simple and scalable predictive uncertainty estimation from deep ensembles. They have to have a comparison, or they have to have some metrics which they are computing to tell that their uncertainty estimation is good and better than the others. Right? So there are a few set of techniques which exist. In fact, if you look at this repository from Google, high quality implementation of standard and state of the art methods on a variety of tasks. So they have specific best practices for uncertainty robustness benchmarking. So if they're measuring uncertainty and robustness, they have to have those set of metrics well defined. They have a few data sets, a few models, metrics. Test, calibration error, as we were discussing, right? We can have a calibration error. We can have negative log likelihood. Under certain assumptions, you'll have to put a likelihood. And train and test runtimes, right? So if we look at these metrics, of course, for the third and the fourth point here, we will have to actually run the model, right? But with respect to the fifth point, train and test runtime, how would you compare How do you compare the last three methods? Which of them takes the maximum least training time, okay, in the last three methods, C, D, and E? How many say C? Least training time, okay. Any guesses why?
I think D takes a lot of time because
Training, we're talking about training. So in C, we train multiple models independently. In D, we train a single model. In E, we train multiple models independently. Which of them should take the least time? D, right? Which of them should take the least time in prediction? Okay. The best answer to this should be I do not know. Right? We do not really know here. Assuming we do the same number of forward passes and the model is exactly the same, they should be taking the same time, right? Because each of them is now going to be doing forward passes. Wait. In MC Dropout, we need to do a forward pass across a single model, and in Ensemble, we need to do forward passes across multiple models. Typically, the ensemble size is small. It may be 5, 10, 15, 20 models. Typically, the number of forward passes for MC Dropout is huge. It is larger. So, in that respect, maybe C and E will take lesser time for test, right? But if we do an equivalent number of forward passes, they should be the same time. But in training time, it's very clear MC Dropout is efficient. Other questions? Okay. So, I will be now showing some data set. Okay. Why am I using this data set? Rishabh? Now, we have to talk about uncertainty, but why for uncertainty quantification might we want to use a data set like this? So, I think thinking from the invigilator or the teacher's perspective helps you a lot in such questions.
what higher uncertainty in the region where you
Good. We have certain regions where the density of points is 0, certain regions where it's more dense, certain regions where it's less dense. In the regions where we don't have data, we should be very uncertain about, right? So, therefore, we have specifically picked up an artificially curated data set. Right hand side, a lot of density of data points, we should be able to fit well. Left hand side, sparse, in middle, no data points. I will be creating a simple MLP without using nn.linear. I have W's and B's and W's and B's across 3 layers in fact here. Right. So, I go from input dimension 1 to 100, 100 to 50 and then 50 to 1. Right. Again, why am I not using nn.linear? Am I just showing off that I can implement it without using nn.linear? What could be a good reason to not use nn.linear? No, we will be using biases also, but good attempt. Yes. We may be setting some weights to 0. Why? For dropout, right? So, I wanted to show how dropout works. That is why I removed nn.linear. But typically, once we have looked at this lecture, I think you should be using nn.linear and nn.dropout. That would be ideal. But for learning purposes, I think at least once you should use this. Even just setting this nn.parameter of torch.random, etc., this took me a bit of time because I kept getting this error, non-leaf nodes cannot be optimized, something like that. I believe some of you might have seen that error in PyTorch. You have to be careful about the computation graph. So, you have to be careful where you use a parameter, where you use a tensor, where you use requires grad, where you don't use requires grad. And you have to be special careful when you are doing things on the GPU. Right? So, these errors came, but this is a simple model, 1 to 100, 100 to 50 and 50 to 1. Right? And I get all these set of parameters. I define my MLP as follows. It takes x as an input, it takes the parameters, and it has a method p equal to 0.0. Why is it grayed out? Why is p equal to 0.0 grayed out? P, unused variable. So again, there seems to be a bug in the code. Why would I do that? But I'm not using it here. I will use it later, right? But if I'm using it later, I'm not using it, why do I still need to keep it here? Now think software engineering. What is that I will do repeatedly? Train. Right? In train, I will be passing a function. That function has to have the same signature unless you want to go in the keyword arguments and arguments, right, setup. So this is a simple setup. W's and B's you get as params. You basically unpack them. You do the first layer activation, h1 equal to torch.tan h x into w1 plus b1. h2 is equal to the second layer. You do the same thing and then dot travel. Why am I doing that? Sorry? Okay, so typically we don't have a ravel outside, right? Or we don't have a flatten outside. Let's delete this for now. I have a train x, train y, I move them to some data set, I move them to the GPU. I create a test x which is minus 2 to 8 and none. What am I doing with this line? Why all of a sudden none? We are expanding the dimension, right? So we could have done this as reshape minus 1 comma 1. Right? So we are expanding the dimension. Test x we have created. Now, as I've mentioned many times earlier, it's a good practice to always show the untrained model, right? To see if everything is working correctly or not. So let's see the untrained model once. And the untrained model is as expected bad, right? Now, if you don't play around with the untrained model, you don't do enough of experiments, you may not know that here using tan h worked out better for me. The default choice is obviously relu, but here for some reason, for various things, this turned out better. Then I have a simple MLP. So this is the reason I wanted to show the I wanted to use a same function, because in the train function I am using the forward function or the MLP function, which is the forward pass to me for me. Right. Now let me just train this. This is the function. I will get the parameters, I will create an optimizer object and I will train. The loss is stuck. What is the reason? What could be that warning? How could we do gradient descent and not get any shift? Did we start off as very lucky? No. User warning, using a target size 600, that is different to the input size 600, 1, right? So many times when you have such bugs and you are not careful with the outputs, this is the mistake that you'll make. Now I'll change this back, the MLP function back, to flatten this out. Everything else remaining the same, and the loss is converged quickly. But torch.nograd, why do we typically call torch.nograd? Anyone? Can you be a little louder? Yes. We call torch.nograd because if we don't do that, y hat trained equal to MLP of something, it will create more nodes and edges in the computational graph. So we want to create a computational graph for only those things where we want to do a back propagation on, but on test data set we are not doing anything. So might as well save that memory. Right. We then just plot the predictions, and it seems the predictions are okay, fairly good. Right. You have data here, the predictions are good. You have data, the predictions are good. Here it's okay, it's not that bad. It's close to that function. Right. Now, deep ensemble is a very simple concept. I am not doing anything significant here. I have 5 members in the ensemble. Right, I have my 5 members and I am just training each of them for a few number of iterations. For the first member, the loss has already gone down close to 0. Second one also the same. And then I'll plot that, and it comes out to be something like this. Right, you are seeing these different predictions across the different neural networks. Right. What do we learn from this? What can we conclude from this? Okay, Ritik.
Where there is no training data, there is much more discrepancy in the
Okay, excellent. So at the test X, where we don't have any data, we see slightly more variation in our predicted distribution. In fact, for some particular seed now, if you see, it seems there is a lot of difference here also. But if we look at the uncertainty shown in this yellowish color, we see the uncertainty is way lower here and way higher here. Right? But importantly, I would also suggest that whenever you make such plots, sometimes they could be a bit misleading. Also make a plot like this, which shows uncertainty independently. Right? So here we can see that there is some amount of uncertainty here, there is some uncertainty here, and so on. Right? Importantly, we have the highest uncertainty in the region where we don't have data points. Okay, any question in deep ensemble? It's just a simple concept. You train multiple independent neural networks on the same data set and you predict on each member in the ensemble, and you will get a variance in the prediction and you use that as predictive variance. You could do the same thing with the random forest also. Now the next topic we will be discussing is dropout. Have we used dropout earlier? How many of us have used dropout earlier? Seems a very small number of us have used. Why do we typically use dropout? To prevent overfitting in neural networks, right? That is where dropout was being introduced. And again, you may be surprised, I don't know to what extent you'll be surprised, but it's a very recent paper. It's not a very, very old paper if you look at. If you look at dropout neural network, I think it's from Srivastav. Right, so it's a JMLA paper cited 46,000 times, but published in 2014, less than 10 years old paper. And Jeffrey Hinton, Alex. So if you look at the authors, many of them you may already know. So this is the main idea of a dropout, right? You have a standard neural network and you remove certain nodes from this neural network with a predefined probability. Why does that work out better for regularization? some weights turn out to be 0. Okay. I will not give all the detailed answers. You should look into either read this paper, or if you want a quick summary, go through Andrew Ng's lecture on dropout on YouTube. Should be fairly quick. But this is the main idea. You want to drop out certain nodes. Right? Now, dropping of certain nodes, does it mean that we change the neural network at each iteration? Yes? No? Yes and no, right? If we change the neural network at each iteration, wherever we apply dropout, it is a very expensive operation, because you have to create the computational graph again, a different computational graph. Right? What could we instead do? We zero out those nodes after the activations. So that's the main idea. So what we'll say is that we'll get certain values of activations on each of these nodes, but instead of using those, we will just we'll consider them to be zeroed out. So now we'll be looking at dropout, and we'll see if we can implement this from scratch. We are not talking about uncertainty for now, just dropout. So I will be now using a simple, now I will be showing you why I had used the W's and B's. I get some W's and B's, I get my first layer activation, right, which is test x into W1 plus B1, and I apply the activation function on that. So I've got the activation. If I look at the shape of this, this is 1000, 100. What do you think 1000 and 100 here mean?
100 neurons, and the data set size was 1000.
Okay. The dataset size was 1000 points. Test X has the size of 1000 and 100 nodes in this hidden layer. So therefore you get 100 activation of vector of length 100 for each input, and you have 1000 such inputs. So the size of H1 is 1000, 100. Now what we're saying is that let's assume that the probability of dropping out of a node neuron being dropped out is 0.2, right. So you're saying that 20% of these you will want to drop off. So what you end up doing is we create not 20% of neuron as such, 20% of the total number of elements of this 1000 cross 100 we can drop off. Right. So what a simple way to implement that is we create a mask which is a binary mask, either true or false, and whose shape is like H1, right, and we see if it's greater than P. Right. And that because of the property of uniform distribution, this being greater than P is, you can figure out the probability. Right. So therefore 80% of these samples will be not dropped off and 20% of the samples will be dropped off, which is less than or equal to P. If we look at the masks, right, so about out of these number of 100,000, 1 lakh, we are left with about 80,000 of those which are not dropped off. So what is H? Can someone tell me what is H? Right. So consider this to be just one example for now. Right. Let's consider a single test X. Right. What would be the shape of that? 1, 100. Right. Out of that, you may end up dropping how many? 20 nodes, right, out of those 100 nodes. Now you just have for each example, what you're saying is you may end up dropping different nodes, right. So therefore the masked activation that you will get is H1 into mask, right. The mask was of the same size, but the mask is a structure which is either zeros or ones, either falses or trues, right. So we can actually see the setup here also. We have 100 columns corresponding to the 100 neurons, and we have 1000 such rows. I'm just showing the head, 5 rows, and about 200 of such entries would be trues or false. And this is the binary mask that you get. You will multiply this with the current set of weights, right? And interestingly, even before we applied dropout, some of the columns were containing a lot of zeros, right? But now let's look carefully. I will have to zoom out a bit. It's a false corresponds to 0. So if this is my mask matrix and I have a false here, I have a 1.8 here. If I multiply these two, what will I have at this 0th row and second column? 0. And we can confirm that, right? So this is what the product of H1 and the mask will do. So you have to calculate this mask for each such layer. We do this, right? And so then I am showing the code for doing this. W's and B's equal to params. H1 equal to torch.tan h of x into W1 plus B1. And I have a flag of called if training. Right? So first to the mask computation, do H1 equal to H1 into mask, and then I do H1 equal to H1 divided by 1 minus P. Can someone tell why are we doing the 14th line here? Right. So we are removing some percent of the nodes. If we look at the expected value of H1, if we didn't remove these nodes, right, it would be different. So this becomes an unbiased, this becomes a biased estimate if you don't divide by 1 minus P. Think of this as just unbiasing or debiasing the activation, right. So if you do H1 equal to H1 divided by 1 minus P, you are scaling it up again. And then you again do H2 equal to activation and H1 into W1 plus P2 and so on. Now we are doing the training of this model with dropout on, right, which means that I will pick up a certain value of P, I look at the parameters, and my only thing which I have changed in my code thus far is just now using a different function, forward function, MLP dropout. So this was the reason why I had set the P equal to 0 previously also, to be able to use the same train function. Now if I train this, the loss is firstly not going down as quickly as previously, you might have noted. Any guesses why? Each time we end up with a slightly different view of the model, right. So because of regularization we get those effects also, and the loss doesn't go down that much also. And you think of it as you optimize certain parameters, but then you drop off a certain node, and then certain nodes which were not optimized they come back in the next iteration, so on and so forth. So therefore this loss would be generally slightly noisier, right. The loss versus iterations would be slightly noisier. Now we will be predicting here. So again we will have no grad set. I will be doing y hat dropout equal to MLP dropout and training equal to false. Right. With training equal to false, I will be computing H1, right. I will not be doing the masking or the scaling, because training is false. You could also think of it as P equal to 0, right. So you could have actually just done, so you could also just assume training equal to false means P equal to 0, and then these lines are equivalent, right. If training equal to, if P equal to 0, then H1 equal to H1 divided by 1, and the mask torch dot rand like H1 greater than P would all be, you will not have any entries here, right. So then we make the prediction, and doesn't seem like a very good fit, right? So it seems that now our model has underfit a bit, right? As a consequence of using dropout, our model has underfit a bit. What was the purpose of using a dropout? To prevent overfitting. So it means that it generally makes the model slightly more biased, or it increases the underfitting, right, or reduces the overfitting, right? But it seems that the previous model was not really overfitted. Right? If you look at the previous model output, it was not really overfitted. It was okay. It was good. But now, because of the dropout, the model has become underfitted. So what can we then do? We want to be using dropout, but it has already made a model way simpler than we needed it to be. Okay, we'll do what Bhavesh is suggesting, but something else. We can reduce the probability of dropout. We can reduce the regularization strength, or can we make the model more complicated and then apply dropout? We could do that also. So all of these things we could do. I will now show you something else. Now, even at test time, I am setting dropout equal to true, right? Which means that for each forward pass that I do, I will get a different prediction because my model is different each time. If I do this and I plot my model with uncertainty, I have uncertainty here. Do you like this uncertainty? No. Why not?
So firstly, the predictive uncertainty is not very like in the point where there is a high density of data in the very right end, the uncertainty is also very high, and the prediction is not very good.
Okay. So the other thing which I mentioned was, if you just plot the uncertainty, this will become clearer. The uncertainty is almost constant and very high. So I forgot one point. Let me actually come back here. So here it seems the model is doing bad, right? But let's see if I, for some reason, forgot this scaling factor. Let me actually see if I discuss this here or some other point. Okay, never mind, I'll come back to that point again, right. So another thing you could do to make the model more sophisticated, more complicated, to not show this underfitting problem, is to add residual connections. So this is again inspired or borrowed pretty much from the lecture slides which I had mentioned, from the lecture notebook, this one, right. The comparison to other methods of uncertainty quantification, and it's fairly similar, the data set is slightly different. So if we come back here, now if you notice here, I have set the dimensions of all the layers to be the same, right? And I am saying that h1 equal to torch dot tan h x into w1 plus b1, h2 equal to torch dot tan h h1 into w2 plus b2, and h2 equal to h2 plus h1, right. So now I am adding a residual connection, one which goes through, so one path is from h1 which goes into this h1 into w2 plus b2 terms, and is you get the output via the tan h, the other is the h1 is directly fed here, right. So for this we may want to look into residual connections. It's something like this. So h1 goes into this, h1 goes into this function which is h1 into w2 plus b2, you get an output h2. h1 goes into this, you apply the activation, you get an output, or you can also directly feed in h1 here and then add, right. So this is what we can do, and then we do h2 into w3 plus b3, right. Again, I'll not go into too much detail here because that's not the point. Residual connection will end up helping here. We train the model, the loss settles down, and now if you look at the prediction, they look fairly good, right? So we are still using the same-ish model, but we've now added the residual connections, and now we're getting it, the predictions. But at this point, we have not used dropout with the residual model. Right? We'll first try with deep ensemble with residual connections. We'll not see much change because the previous model was already working well. So I can, in the interest of time, I can just show you this particular output, that from the residual connection ResNet like model, if residual connection model, if we do deep ensemble, we get the predictive uncertainty, but that is more or less the same as what we did earlier. Right? So nothing has changed much. But in MC Dropout with residual connection, things change a lot. Right? So we are now doing MLP dropout function, we are modifying it. There are two changes which I have done here. Firstly, in H1, I have not applied dropout. Right? I have applied it to post H2, I have applied dropout, which is here, and then I am doing H2 equal to H2 plus H1. So the rationale was that we wanted to add in a connection which was not sufficiently dropped off already, right? Which was more or less the same set of features being used. So you H2 equal to H2 plus H1, you have two ways of passing in that information. In one of them you have dropout, in the other you don't have dropout, and then you are adding them, and we are scaling it also here. H2 equal to H2 divided by 1 minus P. Now we are training this with P equal to P equal to 0.5. We have set a very, very high dropout ratio now. And it seems to have converged. And now if we look at the predictions, they are better than previous model where we were using MC Dropout. Now let's try and go back and see if it didn't do the scaling. H2 equal to H2 divided by 1 minus P. The loss will still be converging. What do you think about this prediction? Is it worse than the previous one? The previous one was perhaps bad only at the places where we had no data. Here, do you sense that there is some kind of bias which has crept in? That bias has crept in because of this line. This we had commented out. If we set this line back, right. Now, if we set this line back, there is no apparent bias in the data in most of the predictions, apart from the region where we don't have data. And now we will be running 100 forward passes with dropout enabled, right? Even at test time. So if you have, so let's think of two modes in which we run dropout. Right? We're not talking about MC dropout for now. We're talking about the regular dropout. The first mode is the training mode, right? In the training mode, if you drop out certain nodes, right, and you don't scale the activation, whereas in the test time, you're not dropping off any node, right? So the expected value of the activations that you're getting would be different, right? So therefore, you need to have them compensated at the train time also. Let's go back slowly. If I have this line commented out, right, and I'm dropping out 50% of the nodes, right. So let's actually make things even simpler. Let's assume that we are talking about this layer, right. Let's assume that for some particular reason that we had applied something like ReLU, not tanh, and the values of each of these was 1. So, what would have been the sum of these values or the expected value of activation at this layer? What is that? Right. So, we want to be, or let us look at the sum of these, right. The sum of these would be 1. Let us look at the left network. Right. If all of these values were 1 before dropout, the sum of these is 1 plus 1 plus 1 plus 1 plus 1. Now, if you look at, you have dropped out certain nodes. So, you have 1 plus 1 plus 1, right. You have dropped out 2 nodes. So, it is 3, right. So, should you be doing 3 into something to get comparable to 5, right. So, therefore, you need to do some kind of scaling. Right. So, that scaling you need to do only at the train time, because at test time you will not be doing any dropout, right. So, we do that scaling at the train time, and at test time we do not need to do any scaling. And then now we apply this at the test time with dropout on for 100 iterations. Okay, what do you think now? Hey, not ideal, but somewhat better than previous, right. It is suggesting the fact that we have a lot of uncertainty here. The model is of course still exhibiting a bias, because this function is not the same as the function here. So, we need to improve in that respect also. Maybe use a better model, maybe use a different ratio of p. Let us try with those also. We are setting p equal to 0.5, let us make it 0.3, let us say. And many times such experiments we have to run with different initializations and then figure out the one where the optimizer is working the best. So, basically SGD like networks, like optimizers with multiple restarts. Right. So, here again it seems to be fairly similar. Right. So, it seems that there seems to be some bias in our predictions here. We could improve that with a more complicated model, right, or better usage of residual like connections. But importantly, if we look at the uncertainty, there seems to be certain uncertainty which is higher here compared to the uncertainty at the other places, which was not the case initially when we did not have the residual connections. So, we go back to the point where we did not have residual connections. This was our uncertainty and this was a predicted model, right. So, by the addition of multiple tricks that we have done, one, we have used residual connections, secondly we are applying dropout and we are also having some scaling, correct scaling. Thirdly, we are not applying the dropout at the first layer itself, and right, because of these things we are able to get MC Dropout to work better than what it was earlier doing, and therefore, as a consequence we do not have uniform uncertainty. Our uncertainty ends up now being more calibrated, it seems to be more around the region where we do not have data. Right. So, some of these could also be better done if instead of using from scratch implementation, if we had used n and dropout. So, it will automatically do these things better for you. Right. There could be some small bug lurking here or there. Okay, questions on this?
Why is it called MC Dropout?
Okay, good. Does anyone want to answer that? Why is it called MC Dropout? Okay. Anyone else wants to try that?
Monte Carlo was some place in Mexico where there were casinos.
Okay. So Utkarsh just told the history of Monte Carlo, but I don't think that was the question, because that history is, we have discussed that in an earlier lecture. The question was that why is it called Monte Carlo? So Monte Carlo methods have a certain kinds of properties. Go ahead.
So, like, dropout can be considered a probability distribution over the weights, and what we are doing is we are sampling and then taking the average. So that is
Yes. We'll need to go back to this paper. Dropout as Bayesian approximation. Right? So we end up applying dropout. So when we apply dropout, it gives us Bayesian approximation. That's in this paper, they develop a new theoretical framework casting dropout training in deep NNs as approximate Bayesian inference in deep Gaussian processes, and a direct result of theory gives us tools to model uncertainty. So let me take you here.
In a way, when we applied dropout, that was building some kind of redundancy in the network. And then you at test time please drop and generate these results and call it uncertainty. How will that be?
Yes. So to answer this question, you have to start from here in this paper. You will have to look through a little bit of maths, right? So this particular thing that you're seeing, Zij is Bernoulli distributed with Pi. What do you think this is representing? So Bernoulli distribution, dropping off, not dropping off, right? So this is that particular dropping off. You have a posterior distribution P of W given x and y, right? This is the distribution from which if you sample, then you are essentially working with Monte Carlo methods, right? But we don't have access to P of W given x comma y. We end up creating an approximation around that, which means that whenever you create an approximation, you have to either use a method like Laplace approximation, where you assume that the approximate distribution is a normal distribution. Here they end up approximating it to a deep Gaussian process, right? So this is the important line. New theoretical framework casting dropout training as approximate Bayesian inference in deep Gaussian processes, right? At this point of time, we have not studied either Gaussian processes or the specific techniques which they use, which is variational approximation to minimize the difference between two distributions or the divergence between two distributions. And if we come back here, right, so this is what we say, right, typically. Our approximate predictive distribution is Q of y star given x star is this integration. The first term is the likelihood term. The second term is the posterior, right, where omega equal to wi is a set of random variables for model with n layers, right. And then they do these things. We perform moment matching, estimate the first two moments of predictive distribution empirically, and then they have this particular result, right. For the different t forward passes, if you use weights in this specific way through the dropout, they can be thought of as coming in from the some approximate posterior distribution with some certain properties, right. So they have all this maths to show that. But that's the good part of this approach. You don't need to know all of this maths, at least to apply initially. Does that answer your question? So it will be much better understood once we understand the other things, which include variational approximation as well as the Gaussian process. Are there other questions? No other question? Okay, so this is all I had for today's discussion. The next class we'll see there are again. So we have one class now left before the break, right? Your exams start day after, and when do they run till? 16th, which is a Monday. So then we'll not have a class on 16th, right? If you have an exam, then
No, we'll have classes on 16th.
you'll have a class on 16th, but you don't have a class on Thursday. Do you have a class on that following Thursday?
Yes.
Okay, so then we'll have two classes, right? So we'll see what specific topic